As I was saying, today's Light Day, and our guest light expert with us here is Dr. Rick Sellens, and he's a professor in the Faculty of Engineering and Applied Science at Queen's University, which is in Kingston, Ontario. So thank you very much, Dr. Sellens, for calling into STEM Camp today on Light Day. I officially will welcome our camps in Ancaster and Woodstock. Thanks, guys, for joining us. So as we heard, you guys have been experimenting with some light kits, learning about light, optics, visual perception. Sounded like you were doing some things with optical illusions, which is cool. Before we get to your questions about light today, I'll go to Dr. Sellens. Can you tell us a bit more about the types of things you do with light at Queen's University?
Well, I'm a mechanical engineering professor, and most of the people who are interested in understanding the details about light are physicists. They're the scientists that specialize in things like light and atoms and behavior of those things. I'm more interested in light in terms of what it can tell me. And that's probably what most of you students are more interested in light for, is you want to switch on the light and actually see something. And everything that you see every day, you're seeing images that are created in your eyes by the light that passes from some light source, either the light bulb in the ceiling or the sun or wherever the light is coming from, hits something and is then returned from whatever it hits to your eye. And that's what you're seeing, is the light that's in your eye. Now, we use the same sort of approach in measuring things. Sometimes you can't touch something to measure it, like you put a thermometer onto your finger and you might be able to measure something about the temperature of your finger. Sometimes we can measure things more accurately if we just bounce a little bit of light off them and get that measurement. So that's the main reason I'm interested in light. And as a result, I have to learn a fair bit of the physics to do some of these practical things. So that's the kind of thing you've been working on today. You've been producing illusions, and you've been making images with pinhole cameras. If you want to know how the pinhole camera works, you need to think a little bit about the path the light follows and how it makes that image in the pinhole camera. And I've got some stuff I can show you to tell you a little bit more about what I do, but maybe we should start with some of your questions.
Okay,
See where that
sounds good. That sounds good. Yeah. Let's start in Ancaster. Is there a camper in Ancaster with a question for Dr. Sellens?
You're asking what are optical illusions?
Well, I guess by definition, an optical illusion is any time that you see something that isn't really what's actually there. You see something that looks a little strange. And most optical illusions are sort of manufactured in your brain, in that your brain will see two things and make some conclusions about them that turn out to be wrong. For example, let me get a piece of paper here. Just drawing a little picture here. Now, one of those lines longer than the other?
Yes.
Maybe it doesn't look.
No.
I'm not sure I drew it very well, but illusions like this, with these arrows and these arrows in different directions, can fool you about the length of the line that's in between. And that's because you associate those arrows with some stretching or some pushing together. And likewise, other illusions can happen when your brain sees something a little bit differently. But more interesting to me are the kinds of illusions that are generated when we use our measurement tools and they give us the wrong answers. So have you ever watched on television and you see a wheel moving, and although the car or the wagon or whatever that it's on seems to be moving forward, it looks like the wheel's turning backwards? Has anybody ever seen that?
Yeah.
You can hold up your
I
hand.
know.
Yeah. What's happening there is the video, and like the video that we're using today, it's only sampling 30 times a second. So when the spokes move, it's not always catching every single position of the spokes. And if it catches one position like this, and then the next position it catches is a little bit turned this way, it may look like this finger moved to that position and look like it's moving backwards. So optical illusions are usually about either your brain not picking up what's going on or the instruments you're using, like a TV, not picking up exactly what's going on in the world.
Okay,
That
cool.
answers your
That's
question? I see some of you have got water bottles on your tables. I've got a water bottle here too, and this bottle's half empty. So if I look at you through the top of this bottle, we can almost see me through the bottle. And although it's bent a little bit by the bottle, it's still pretty much the same things. The outlines are still in the same places. Oops, there's my ear. It's kind of fuzzy back there. I'm going to turn off now turning off the overhead light will just make it dark. But if I turn it upside down, I get a very distorted image through the same part of the bottle. So before you do that with your bottle, make sure the cap's on. And you see that distorted image? So the light is following a different path depending on whether there's air in the top of the bottle or water in the top of the bottle. Anybody know why that's happening? No. Have you ever looked at an aquarium? Like a fish tank at home? If you stick the net in to catch one of the fish, does it look like the shaft of the net is bent a little bit?
Yeah.
That's because of refraction. That's because the light's bending as it goes from the air into the water and back again. And in your aquarium, all the walls are nice and flat. So all of the light bends the same amount. But on the bottle, the walls are curved. So when it goes from the air out of the water, some of the light bends a little bit, some of it bends quite a lot as it passes through that curved surface. And that's why you get all this distorted image in here. And that's the same thing that's going on when you use a lens, like the lenses in my glasses. They curve the light. So when I look at them like this, I get a magnified image of what's on the screen. And they curve the light in ways that allows me to see that magnified image, or when I put them on my face, to be able to focus on the image that's on the video screen in front of you. So, any more questions?
I'm sure there are. Let's see if there's a question on the
It's a question about you.
Okay, about me.
Have you used lights in science?
Have I used light in which? How long have I worked with light? Well, practically ever since I was born, because I've been using my eyes that long. But in terms of doing more scientific things with light, I started doing graduate studies at the University of Waterloo in about 1983. So that's about 30 years ago. And at that time, I was getting involved in measuring sprays of liquids. And whenever you want to burn a liquid fuel like gasoline or diesel fuel or fuel oil that you might have in an oil furnace in your home, anytime you want to burn a liquid fuel, usually you make a spray out of it first to evaporate it so that you can burn it in a gaseous phase, so that you mix together the evaporated fuel with air and it burns. And the quality of the combustion you get, the way it burns, depends a lot on the size of those drops. So I started doing work on the sizes of drops. And as you can imagine, if you think about a spray can or a cleaner bottle when you pump the spray that comes out there's a lot of drops, and they're very small. And if you stuck your finger in there or a piece of paper in there or something and tried to catch one, you'd have a really hard time measuring how big it was. So the best way to be able to see what's going on in that spray is maybe to take a picture of it, or if you want to know what's going on with one of the individual little tiny droplets, that picture might not give you enough detail, but if you could shine a laser beam on just one drop at a time, then you could better measure how big that drop was and where it was going and how fast it was moving. And that's work I started doing in the 80s, long before you guys were born. And that instrumentation approach with the lasers was fairly new at that time. It's pretty well developed now. Since about 2000, there haven't been too many changes in the type of instrumentation, but it's widely used instrumentation for measuring those sprays and producing better results in combustion. And for example, some modern cars, like my car, have gasoline direct injection engines, where the gasoline is injected directly into the cylinder where the combustion takes place. And that gasoline direct injection requires you to have an awful lot more control over how much fuel, how fast it's moving, where the drops are going, in order to have an engine that runs efficiently but doesn't produce a whole lot of pollution. And that's the kind of development work that the mechanical engineers have done with this kind of optical instrumentation. So yeah, I've been working with optical stuff for a long time.
Cool, that's awesome. Let's keep the questions going. Let's go back to Aincast for our next question.
There. What does light do?
What does light do? It does a lot of things, but fundamentally, if we get right down to it, we can think of little chunks of light. Those are photons, and whenever some energy is released from, it may be something's burning, a candle flame, for example, emits light, or the sun, very hot, emits light, and it emits it in little chunks called photons, and those photons travel very quickly in a straight line unless they are interacting with something else. So a photon might come from my nose, if my nose was hot enough, and go towards the camera up here, and it'll go in a straight line through the air into the lens on the camera, and that photon will land on the detector that's in the back of the camera and have some effect on that detector, because the energy that came from my nose, that photon energy, went out here and landed on the camera and delivered some energy to one of the little detectors in the camera, a really tiny bit of energy. So basically, light transmits energy from one place to another place along a straight line unless it gets bent by something. And it can get bent by interacting with materials like the water in this bottle. So if the light from my nose went out and hit the side of this bottle, it might be refracted inside the bottle and then refracted over to the camera. So I think there's probably some path that goes from the camera through this bottle back to my nose, and light will get bent by interacting with physical things like this. It'll also get bent by gravity. So if we put a black hole over here, some of the light from my nose might pass around that black hole into the camera, following a curved path due to gravity. But most of the time, for practical purposes, you can treat light as going in a straight line unless it interacts with something significant that you can see, like a water bottle. Does that answer your question?
Yes. Cool.
Now,
All
the
right.
more interesting question is, what can you do with light?
Yeah.
Light doesn't do anything particularly interesting, but a whole lot of light traveling through interesting pathways gives us images that we can see and learn things from, and see the world around us. So, for example, I was holding this up before. I don't know if it showed on your screens before. This is our low-tech opportunity to get an image to you. One of the other things I do, so these are organ pipes in a basilica in Barcelona. And, whoops, this is the stained glass that they're reflecting, but because they're curved, they reflect it in a different sort of a pattern. And that's because the light is interacting with those organ pipes, and it's bouncing off those organ pipes from the stained glass window and going into my camera. And because they're curved, it's bouncing from all different directions, for the same reasons that because this water bottle is curved, it gives us a distorted image through the part with the water in it.
Yeah, very cool. Thanks for sharing that. That was cool to see. Let's go to Woodstock for our last question. We're running out of time, but we have time for one more. Is there a camper in Woodstock with a question?
So how much light can we see in our eyes?
How much light can you see in your eye? Is that the question? Okay. Well, your eye has different regions in it that have different levels of sensitivity. And I don't know an awful lot about eyes, but you'll notice that when you go outdoors on a bright sunny day, you can still see everything and all of the color is there and it looks reasonable. And when you go out to the same place at night and there's only a street light on, you can still see most of what you could see during the daytime. And that's because your eye is opening and closing the window through which it sees the world. So if you look at the center of your eye, there's the iris there, and your pupils will get smaller or bigger to let in more or less light. So when it's really bright, your pupils will get quite small, and less light gets in, and you can still see all the colors. When it's darker, your pupils will get wider, and you'll still be able to see the colors. And then when the street lights come on at night, and it's not so bright, if you think about it, most of the color seems to go away. And that's because the cone cells that are sensitive to color in your eyes require quite a lot of light to be able to see. But you still have some others that can see in black and white, sort of grayscales. And the color's gone, but you still get an image of what was there. So your eyes can see all sorts of different amounts of light. And that's a really good adaptation if you want to be able to go out in the daytime and at night.
Yeah,
Does that answer
very
your
cool.
question, or was there something else?
Woodstock? I think maybe maybe that answered their question.
Okay, good. It's too
All
bad we
right.
didn't see London, but
I
I'm glad that
know.
everybody else could make it.
I'm glad too. I don't know what happened in London. That's unfortunate. But I guess that's all the time we have today. It's already 2:50, so thank you very much, Dr. Sellens, for calling in STEM Camp today and answering all those excellent questions. Thank you to the campers as well.
Okay, well, thank you. And campers, when you go on studying light and studying other things in science, I'd like to encourage you to think about not just that it's really cool, because science stuff is really cool, but also to think about the ways that you can use it, the ways that you can do something useful with the scientific things that you're learning. And that's essentially what engineering is about. It's taking those cool scientific ideas and translating it into doing something practical, like taking a picture or improving the way your car operates or creating solar energy, which is a whole area of optics that we didn't even get into talking about. So enjoy the rest of your camp, and good luck with all your science stuff.